Hi. Um, Thanks for the quick intro, and thanks for having me here. Really excited to be talking about different dimension of data engineering today, which is the price streams at scale. So, as you all know, before I start, so that I have some context, how many of you know what INDmoney is? Okay, a few people. So we are a financial, portfolio. We started as an entire financial portfolio tracking system, and then later we evolved into multiple transaction systems, including the Indian stocks, US stocks, and everything else. So today I'm going to touch upon the most important or the challenges that we faced as we started scaling this price streams. And as you all know, I'm sure even if you don't know INDmoney, I'm sure a lot of people here would know why it is important for the prices to be streamed at a millisecond level granularity and then at low latency for making the pricing decisions on stocks, right? So I just wanted to touch upon a few business use cases before we jump in the technical stuff. So ideal thing is that we should be having super low latencies. There's humongous amounts of data coming in, about 0.5 million ticks per minute, and that kind of goes to about 2.5x on any peak days, some event days, some budget, or some sort of an election results and everything else. So we need to be able to be extensible for that. And we also need to be able to power the charts using the same data. We also need to be able to power the charts, and then those charts are very important for the traders. One, to be able to make the trading decisions, and also to look at how the market is moving, and then historically a lot of stuff. And also in the charts, one important thing is that we will end up having a lot of granularity at which the candles have to also be powered. So it's a bit of high quality data engineering problem where you will want to get the data. You already have the data, and then you want to slice and dice it into multiple different candles at different granular levels. And of course, one important thing about any system also is to be able to give the price alert. So whenever user hits a price point, he might want to get notified for his trading decision. And that they could be of multiple types. Okay, if I hit my stock at A value, alert me, and then, or if it could be, okay, if my stock changes at significant movement of 2.5% up or down, please alert me. So these are all the two important things, and obviously you know that I can't afford to send the alerts to the users a little later as well. And of course, one interesting thing that we've come up with is the AI chart pattern detection that I'm going to talk about a little later. But if you have seen, so this is obviously a typical any stockbroking app, and then we have lots of data coming in all the time, and then there is lots of different widgets inside the screens. So humongous amounts of data, both from the receiving standpoint and also from to be able to be served on the client standpoint as well. So so this is the chart pattern that I was talking about. And with chart, you see that we do power users with some sort of a patterns using AI. And this also needs to be fed the same real-time data that comes along. And then users can make their trading decisions. Here is a bearish pattern, some broadening rising wedge, or this is like a cup and a handle, like a bullish chart pattern. So the point here is there are lots of use cases that are required to be done for a trading system to be able to power using the single source of humongous amounts of stream data. Now, how do we solution in this, right? So what are the infrastructure strategies that we have employed to be able to make this reaching the end users with millisecond latency? Of course, there is a lot of fallback engineering. So the ideology here is that because this is a system where reliability matters the most, right? I can't afford to even go down for let's say a minute or a few seconds as well, because that particular trading opportunity is gone for that user. So a lot of fallback engineering is also required, in the sense that both at the source of receiving the data from the source, and also to be able to show it on the client devices. So for us to be able to build this fallback engineering, of course, multiple microservices, decoupling of them really helps. So I think I was talking about all those 4 different use cases out there. So all of them could still be powered using one single monolith, because they're all similar use cases working on the same data with different things. The other way of looking at it is to try and decouple them into multiple microservices. So what we have done here is, instead of doing it as a monolith, which is not wrong to do, what we tried doing it is independently deploy all of them as a separate microservices. The advantage we get with that is, let's say if streaming service has to go down for some reason, there is this chart builder service which will still run and then build the chart. So reducing the damage of a downtime as well. And of course, there's a very important concept of multicast groups, slightly on the networking. I don't want to go deep into the networking side of the things, because this is purely data side of the data engineering side conference. So I wanted to touch upon what multicast group is, how it really helped us to be able to scale our systems to the amount of high scale throughput that we get, and at lower latencies. And of course, what is the choice of language? So typically with data engineering, there is always one single way of doing things. People pick up one language, say Python or anything else, and maybe some Spark jobs, and then try to ingest the data and then push it to some data store. That is a typical way of looking at systems. What we tried imagining is zoom out of this entire ecosystem, try to reimagine, hopefully in a different way and in a better way, and then give the better control to the users. So this is the multicast group that I'm talking about. So for people who are interested here about stocks, the price sticks originate from exchanges, and then there is this concept of multicast. So a lot of brokers are all there here in the country, right? So all of them will be receiving that, right, through what is called as multicast, through an on-prem infrastructure. And then from then, now for us to be able to power the data to the end users, what we in today's world want is to be able to power from the cloud, right? So you don't want to, you have lots of capabilities of doing it in cloud, so let's not go deeper there. But ideology here is, if I have to run my services in any cloud like AWS or GCP or anything, let's say I unicast into another server on AWS, and from there again unicast it to what is called as a multicast group. So there is a concept of multicast group in AWS or any cloud per se, which allows you to have, let's say if I can have, let's say 3-4 EC2 instances inside that multicast group, and then every machine starts receiving the data that is being fed. So invariably, what my server on the on-prem setup is receiving is being received by all 4 systems. And if you see here, there is no other additional hop. Let's say one system sending data to the other. It's just basically directly through just pure play networking being received on all 4 different servers. So of course, the choice of language is also something that I've touched upon. So when we started using Golang, obviously we wanted to ensure that we are doing it with right configuration and then able to serve the users at scale. So what is the optimal number of Go routines, and then how much infrastructure is required for us to run this application? All of that matters. And of course, we built the WebSockets on Gorilla's framework, which helped us stream the data to the end users very fast. And this is very important thing where people should know how much profiling actually happens on your memory, from your memory standpoint, on CPU standpoint, or even Goroutine standpoint on any of your services. So people have really helped us to a large extent on that. So the beauty here is this humongous amounts of this data that is being received and to be served to the users is all being served through very, very minute infrastructures, which is small infra workloads, operating, probably a couple of our smartphones are even much bigger than that in terms of infrastructure. So yeah, this is one of the ways how, so when we were emulating lots of data, obviously there is a lot of computation and then also lots of connections. So because of that, there is a lot of CPU utilizations and all of that. So when the CPU utilization was checked in one of the cases, we saw that it was hitting the roof. And then pprof really helped us to nail which exact code block was the culprit, and thereby help us optimize that. So the other way of looking at it is throwing infra to the problem, right? So whenever a problem happens, throwing an infra to the problem versus trying to understand what is the particular code block which is causing the problem and then trying to fix it. Okay, what are the other strategies that helped us to do this, right? So apart from the humongous amounts of optimizations that is done, there is always this network where people have to still receive that through the external networks on their devices. So we did a lot of accelerated smart routing. So there is this Argo smart routing from Cloudflare, and then there is also this smart routing. We use MTLS. So with all these configurations, we were able to get to a state where the data reaches the end users in shortest amount of time. I was also talking about this multicast group previously. So with this multicast group, what we are able to achieve is separation of concerns. As you can see, there are 4 different microservices, each of them responsible for doing something different altogether, and then 4 of them being independently developed, and then it's not like one system sending the data to the other. So there is no networking hop per se. So with this ideology, we are able to reach the end user all the way from the exchanges to the end user in very good latencies. So these are all some of the metrics. So we reach all of our 90% of the price sticks to the end users in about 200 milliseconds. And this same thing, the same ideology applies to any streaming systems, not just price streaming systems. So price streaming is one of the use cases that I wanted to present today. But the same thing could be for any streaming systems. It could be for video or audio streaming, or even the price streams that we are doing here. Yeah, coming to the streaming frameworks which helped us do this, there are multiple streaming frameworks with which you can power this data to be sent from the backend systems all the way to different backend systems and also to the end user client devices as well. So we use NATS, open source framework. I'm a big fan of open source. And so what we did is we just tried reading the documentation, understand how NATS helps us set up the very reliable infrastructure. So it provides a very good, high available cluster with which we will be able to stream any amount of data, any kind of data. So here we were streaming price data, but anyone can stream any kind of data where there is lots of data coming in which has to be distributed to humongous number of clients. And of course, the documentation, through open source, you can actually read the kind of code to understand how it behaves. And also there's a lot of good amount of documentation about how to use the libraries from the integration standpoint from the backend and also for the client libraries. And it can be set up in a couple of days without much of an effort. We were able to do that. And then it also supports JWT auth out of the box. So it really helps us in a lot of ways to be able to set it up. Of course, like I said, we learned that the fallback engineering is the best way. So what if this cluster goes down? I cannot afford to go down to my users, right? So we also have a WebSocket server built in-house as well. So this is also used for streaming. So this is like 2 paths, right? A versus B. And like I said, we were using Golang, so we used the Gorilla framework, which also helps you easily build WebSockets out of the box. So with this, you will be able to, again, use this framework to transmit any kind of data with sub-millisecond latencies and still be extensible, right? So I have a couple of learnings I wanted to share here is, of course, there is a lot of map kind of a data structure that is required any point of time because you have lots of data coming for a stock and then you want to send it back to the users who are subscribed to that stock and everything else. So there is a lot of whole bit of operations on map. And then when you have writes and reads on the singular data structure, you always have what is called as you know, the mutexes, right? You want to lock and then unlock and then everything else. So those eat a lot of resources. So wherever there is humongous writes and not as many reads, as many reads as the writes are. So sync map actually does a good job. So it helped us save resources by about 75%. So which again, like I said, these are some of the concepts which helped us to run on a very low infrastructure with very good latencies. And we used network load balancer again. We used network load balancer quite heavily to be able to load balance among multiple different nodes. The advantage of using network load balancer again is that OSI protocol, so that you know, if you are using an ALB, there is always this application layer coming in, a few milliseconds latency. So every millisecond matters. I think that was the theme. That was the theme of that talk as well. So how do we ensure that we are optimizing on every millisecond? I'll quickly run through a couple of important pointers on the tracking of latencies as well, because in the data streaming kind of services, streaming is one part of the things. How do we know what kind of latencies are, how is my data being served at what latencies? That is very important. So we did a lot of optimizations on this through payloads with, you know, when we converted the JSON into protobuf and all of that, we found that it was 50% better or even more. And then one of the most important things is people often get used to look at their CPU memory and all of the utilizations on AWS. So what we learned is when you are using data systems, data streaming systems, a most important thing is to see how much network also is being utilized, because every instance comes with X amount of you know, let's say 10 gigabits per second or anything, X amount of network capacity. So keeping an eye on that helps. And also the APM monitoring through backend latencies, this everyone does. And then most important thing is how do we sample, how much time it's taking for the user. You can always sample some of the data received on the client and then have it instrumented through some APM tool, but you need to look at the fact that not every clock in the world is synced. So you need to do some bit of clock sound, you know, time adjustment as well. And then of course we use quite a bit of Redis ZSet and all of that to be able to, and kind of skipless kind of implementation to be able to power the price alerts for our systems as well. So a few takeaways: common sense engineering, rather than you know, trying to read too many books and then trying to come up with very complicated solutions, simplifying systems. Fallback engineering, always have something or the other as a fallback so that you don't end up running in disasters, and also be prepared for any disasters in case something happens, right? And yeah, of course, the last but not the least, I wanted to highlight the fact of making systems simple, architecting systems with simplicity than over-engineering them. So on that note, I wanted to leave the floor open for any questions that you may have.